for the online attendees will be starting here in just another minute as people come in. Thanks. If you have any online questions that we don't get to during the session, we always email those on to our presenters. So don't feel like if you don't get an immediate chance to respond, you're out of luck. We always record those and then send those questions on. So even if they're being answered immediately, you should get an answer at some point. All right, we'll get started here in just a minute.
I'm going to go ahead and get started here. For those of you who didn't see it, there's a sign up at the table where the food is. If you want to get recognized for having attended this, it's also very helpful for us for keeping track of who's here and from where. It is on. Okay. Can you hear it? Okay. Thanks. We like to welcome Rod Bates from KieranTimberlake, came out to join us today from Philadelphia. And he is going to be talking about the development of accessible building monitoring, although his role at KieranTimberlake is quite varied, and it's really assisting the architectural design teams at many different levels. He has a bit of a different background from a lot of the traditional people and roles found in firms, from history originally, and then moved into the forestry department at Yale, which is a very old program, very well recognized, and branching out really into natural resources generally, forestry as a sort of ecological system, and I'm sure you can fill you in much better than I can on that. He also has been instrumental in the recent development of a program that they call Tally, which is a really designed to work with and in Revit. He also does BIM and other really thermal comfort, performance of buildings. And I'm sure if you have any questions about Tally or perhaps about Revit generally, about how to incorporate these sorts of programs into your practice or how they did it at KieranTimberlake, he can address that as well. Also like to say thank you to Idaho Power, as usual, for helping sponsor this, for sponsoring BSUG and a number of other programs here at the lab. And if you have any questions about that, Sheree and Chris, I'm sure would be happy to answer those questions as well. Next month, Damon from the lab is going to be talking about his newest project, which is sort of a pre-commissioning using modeling systems. So join us next month on the 18th for that. We'll also have a chance at that point to think about next year and what topics, speakers, and ideas you have for planning. And welcome to those of you on the web. Good to have you here. So if you'd like to add anything about your bio or things that I didn't get quite right, please correct me or add to it. Otherwise, welcome. You're on the floor.
Okay.
to get right into it and talk about something that I really enjoy and been involved in for quite some time, and that is building monitoring, and how we as a firm have gone from viewing building monitoring as something that ends up being fairly expensive and very discreet in an application to something that can actually be incredibly rich in the amount of data produced and actually low cost. For us, we see this issue of low cost and high density as being absolute necessities in the context of the built environment. We're not talking about building aircraft here, we're building buildings that are, one, really large, and two, cost matters a lot. So with that, I'm going to take you all through the evolution of the KieranTimberlake monitoring review, and perhaps it gets back to the fact that one of my earlier degrees was in history. Understand the path to bring you to the present. And it all started in the Yale Sculpture Building, where monitoring at it in a roundabout fashion. This client wanted a building that was light, airy, accessible, sort of like this glowing beacon for the surrounding area. But they also wanted to have incredibly high level of environmental performance, and actually this ended up being a AIA Coat Top 10 winner. So really sustainable at the same time, and you can't do that just with any sort of normal custom curtain wall that incorporated to the glazing. However, our insulation in the cowl wall manufacturer was incredibly concerned about excessive heat by the cavity of that curtain wall and whether or not it would exceed the temperatures that were allowed by the warranty. So we actually got into monitoring from a slightly different route there. We were actually looking onto warranty issues. It's pretty prosaic, but those are something that can have really significant cost implications if everything goes pear-shaped. So what we did is we deployed an off-the-shelf outfit, hardware, something we actually, we didn't have a lot of familiarity with this type of technology at the time. So we looked to someone else, for these turnkey solutions. And so we picked up a number of hobo loggers, very simple to use, very easy, no telemetry. You have to go up there and download, but no problem. We can handle this. And we're able to monitor those the curtain walls and find out whether or not we are exceeding the temperatures. And we found out a couple of things. One is that they got exceedingly hot before we put in some shading devices. And then after we installed the shading devices, you can see there on the right, we got quite a bit cooler. And the temperatures that we saw were actually under the 140-degree limit that would have avoided the warranty. So in this sense, the idea of monitoring was actually validated. There ended up not being any failures. And of course, if there had been, we would have had the data to sort of get ourselves out of a hole there. But it also whetted our appetite for doing more of this. And a project shortly thereafter came that was the Cellophane House. That was a continuation of the Smart Wrap Pavilion that we did for the Cooper Hewitt National Museum back in 2003. And the Cellophane House was actually built for the Museum of Modern Art in 2008. And it was intended to exemplify the next generation of flat pack housing. And we looked at it as an opportunity to engage in experimentation on a number of levels. Bring in life cycle assessment thinking, bring in new means of off-site fabrication, on-site assembly, and on-site disassembly, and also, of course, building monitoring. We wanted to know whether or not, if we really wanted to push the envelope, so to speak, and start to think about very different materials for construction, how would they actually perform? Was this sort of a pipe dream to think of a building that could actually substitute brick for layers, basically membrane layers of plastic? Well, we figure one of the ways to do that is to start to really interrogate, these types of materials and actually an embodied or embedded experiment. And part of that experiment was some systems like this. Okay, maybe we can create a cavity inside the envelope that would actually allow the hot air to vent, because we expected a building like this deployed over the summer in New York to get pretty toasty. So we thought, okay, how can we actually cool down this envelope? So it's one thing to draw wishful arrows. So what we did is we developed a monitoring platform, once again using someone else's equipment, the Hobo sensor suite, and deployed them in the building envelope there. And what we hold does this building get? How responsive is it to outsourcing? But also to understand whether or not this idea of this thermal cavity, this venting thermal cavity, could actually function. You actually see the hardware deployed. And you It's clearly not something that's really made for architectural applications. It's something that's, it's a little more scientific in its appearance. But the other side of it is, you're only getting a very small number of data points. We have on every floor. That's not a lot of data. But part of that comes from the fact that this stuff is really expensive. It's about $80 or so a data point, which may not sound like much if you're building it out of Bosch Rexroth aluminum framing, but money still matters. And when you start also thinking on the context of buildings, $80 a data point, and that doesn't even include how you're storing this data, pulling the data where the bulk of the cost comes from, because none of this stuff allows for telemetry. The cost for analysis really starts to go up pretty fast. But regardless of that, and we started to look at, among things, whether or not some of the films that we had been provided by one of our partners actually performed as advertised, which is a film that was intended to reflect out heat, basically being low E coating. And we were actually able to determine in some contexts that this film actually opposed to reflecting energy. So it didn't necessarily perform quite as described. We were also able to assess whether or not this building was comfortable in the city or in the summer in New York. Okay, that's no problem. And so the big question was whether or not we created a virtual greenhouse in Manhattan. We were happy to see that we didn't, but we were also noting that in many ways we were really at the mercy of the diurnal cycle. So in the sense of had we actually created a building that was uncomfortable, perhaps not. Had we created one that was comfortable, well, perhaps not that either. So it was a good opportunity for us to basically validate, or in some ways invalidate, a particular technological conceit. So with that experience under our belt, a new opportunity came along to think very differently about monitoring and really bring it into the realm of a bit more of an experimental mindset. And this came because Yale University was very interested in understanding the potential to modify a lot of their existing building stock to bring up its energy performance. They have an enormous number of buildings. They all consume quite a bit of energy because they're quite old. But they also have a certain aesthetic that is of the utmost importance to a lot of their alumni. They write checks because when they go back to school, it looks like what they remember, and it's beautiful. And the idea of replacing these wonderful, poorly performing buildings with something new is something the university simply would not abide. So we were confronted with this when engaging in a renovation. You're seeing there a trash bag covering a leaky portion of the envelope. You have your single pane leaded glass windows, things like that. I mean, that's not a thermal bridge. That is a thermal superhighway. So it's one of these things where we're confronted with this. How do you respond and how do you adapt to find out what the performance will be? But at the same time, when you begin to make modifications and say add insulation and things like that, what is the effect actually going to be on, say, dew point and freeze thaw cycle in that envelope? Are we going to be unwittingly decreasing the overall lifespan of these buildings? This sounded like a great opportunity for experimentation. So the first thing we did is we picked out several rooms within one of the buildings that they gave us and cooked up some modifications. One where we keep the standard envelope. You have your terracotta and your masonry. And then other ones where we remove that and put in some insulation as an attempt to basically increase performance somewhat. So what we did is we made those modifications, but at the same time we developed a sensor package that once again pulled from off-the-shelf units. So agricultural supply for the weather station. We actually used concrete maturity testing for a series of thermal probes that would go into the envelope to let us measure temperature within the envelope. And then once again using the onset monitors, the HoboWare. Using this information, we were able to assess temperatures over the course of a winter, where we could see with the addition of insulation, the obvious happened. We saw a lot lower temperatures in that envelope. But while this was certainly indicating that the performance that we wanted was there, it did indicate a couple of things of note. One is that our temperatures on the inside became quite high, but also we were finding that our dew point was indeed migrating inwards inside that building, and at times the dew point temperature would coincide with freezing temperatures. So we were seeing, when you started to insulate these buildings, you were starting to see a cooling down of that masonry and the risk of having basically a freeze-thaw incident. The other thing that we noticed within this, by the way, is this supposed to be auto-advancing? Well, it is. I guess it'll keep me on track. The other thing that we noticed with this is that there was a location of a steam pipe within the building below a lot of the rooms we had modified. And we were seeing excessively high temperatures within this space. So as a result of that, with our modifications, because none of the other basic mechanical and infrastructural issues had been addressed, we're seeing excessively high temperatures within that space, ones that really made it incredibly uncomfortable. So through the monitoring, we're able to find out that basically, yes, you can do this. B, you incorporate some risk of increased weathering. And lastly, you have to worry about the overall infrastructure. You just can't throw up insulation and call it done. You actually have to start thinking about things like steam pipe location that might be actually right underneath your building that will be running all year, not nearly or not only just in the wintertime. So given all of this experience, a couple of things that we learned. One is that actually going up to some place and downloading data is a huge cost. It's probably half the cost associated with all of these deployments. And that really started to cut into this idea of low-cost monitoring if you actually had to go there. The second thing we found is that the cost per data point is prohibitively high. You're looking at $80 or $100 per data point, and you're not even getting telemetry at that point. So we realized that as it was, pulling things off the shelf and using them for our purposes was not going to get us to where we felt we needed to be from a monitoring perspective. And I guess the last thing, of course, we realized too is that everything we were using was really ugly. And if these were going to go into clients' buildings, having a bunch of wires sticking out of a wall and things taped up and whatnot, it's just not going to fly. We had to start thinking a little bit harder about how we're going to pull this off. So we engaged in our own development cycle. And so you're seeing at the very top, something that looks like every sort of Arduino system out there in the upper left, and that we slowly evolved into our own platform. And when we felt like we had something that was appropriate, we actually had a project that was appropriate for potential deployment. And this was a project that was done with the Department of Energy and Penn State University. And it was a consortium that was put together to basically explore how they could improve the energy performance of existing building stock by over 50%. And sounded like, well, there's quite a challenge. And it sounds like a perfect one for a monitoring application. So to determine whether or not this was feasible, and also as a demonstration, they took a building that was in the Philadelphia Navy Yard and made that their first test case. So this building was, I think, what probably people that restore cars refer to as a basket case. It had been unoccupied for about 20 years. It had been a former recreational facility for the Navy, and it was in a tough spot. It needed a lot of love. But one of the things that we needed as a team was to understand how this building was actually performing. We were getting something that basically hadn't been occupied for 20 years. There were no bills to look up. We had no idea how much energy this building would consume. But one of the primary goals of this consortium was to understand and prove that they can improve the performance of this existing building stock. So to reconcile this, they felt it was important to devise an experiment, one in which we began to wrap their heads around, in conjunction with modeling and more standard practices, the energy performance of the existing envelope. So to do that, they devised something that was pretty unconventional, and I don't think I'll ever see a client do this again for probably a variety of reasons. But they took a number of enormous space heaters and large propane tanks and got a crew in there to basically heat up this building in the middle of winter from about 40 or so degrees up to about 90, and then cool the building down. And they were going to couple this with thermography over the course of the experiment to understand sort of the state of the envelope. But they really wanted to understand what was actually happening in real time within that envelope, not just sort of a series of snapshots that you were provided by thermography. So they knew that we had done some work with sensors, and so they reached out to us and said, hey, we got an opportunity here for you guys to try out your kit. What do you think? We thought, well, that sounds grand. So we went down there with our hardware and deployed a number of sensors within the envelope in the building down there to understand exactly how it would respond. So using this first generation of hardware that we produced, we installed sensors throughout the building. And fortunately, given that we had prototype hardware, this was a building that was basically to be completely redone, so it allowed us to drill and be messy about our application, and to basically install all of our sensors. And one of the key things that we began to realize with this particular development is the importance of corresponding data with location. And that may sound easy, and it is easy when you have one data point or two data points. When you start to have a lot of data, knowing actually where that data is coming from is surprisingly hard. Every piece of data basically has to have a name, a serial number, or DNA, or something like that that's irrevocable. It's associated with it when it comes in. Because otherwise, all you're left with is a bunch of spreadsheets, and you have no idea where all this information is coming from. So we devised a system that basically used the one-wire protocol, where every data point actually comes with a completely unique serial number from the manufacturer. So every time this piece of data would get pulled and go to our database, it would not only provide you a temperature or relative humidity reading, but would also provide a serial number. And that serial number could be associated there with one of those tags, and it can also be associated with a name and a location in a model. And for us, in many ways, this was one of those big breakthroughs that really helped us when it starts to think about monitoring on a very large scale. You know, when you're able to start moving from just a few data points to really big, this is one of the major breakthroughs that we had. The other thing that we wanted to do with this is start to visualize the analysis. You know, data that's represented just in spreadsheets was pretty dry, and its graphs don't necessarily cut it. But starting to move towards the realm of animations, where you can pull this type of data in from this particular experiment and visualize it, really helped us start to basically wrap our heads around the data, as well as our clients who may not necessarily be as facile with this information. And it ended up being a great experiment. We were able to understand how the building performed poorly, as one would expect, and create that baseline of performance. So somewhat emboldened by that experiment, perhaps more so than was justified, we moved on to our next application of monitoring and high-density monitoring. And well, one of the things you realize is that this type of data was really useful. We were learning a lot of things, and we were also really beginning to appreciate the fact that we could pull a lot of data and get very fine-grained analysis. So what we wanted to do was think about transferring this type of methodology from thinking purely in the context of, say, building envelopes or building science, and start bringing it as a companion piece to ecological assessments that we were conducting. At the time, we had initiated what we called the Green Roof Vegetative Survey. We had done a number of green roofs and always told our clients that these things were creating these thriving ecologies on various roofs. And we were doing that as sort of an absolute assertion of confidence with very little data to back it up. And on one of our projects, I happened to be doing a measurement and verification process, and I looked out over a lower portion of the roof, and I saw the most incredible jungle of vegetation I had ever seen. I thought, wow, there's something happening on these roofs. It does not look like what the landscape architect intended. So with that little bit of an impetus, we went back to all of our green roof projects that we had deployed over the years and done a very finite species count. And what we began to realize is that what we had planted initially was very far removed from what we were getting when we went back. I mean, in some places, there was almost nothing left from what we had initially planted on these roofs. So we began to think, wow, there's something happening here that says, well, A, maybe we shouldn't put so much effort into this really beautiful species palette on our green roofs. And B, what's the actual performance of these roofs? Are we actually selling our clients a bill of goods, or are we still getting a lot of ecological value out of them? So we deployed traditional ecological survey methodologies, pulling from forestry, and broke these roofs all up into 1 meter grids, and then sampled all of the plants that we found within those grids. One of the things that we began to realize, though, is that it was evident that there were drivers for the species distribution that weren't necessarily evident. There's some things we could model, like shading distribution and things like that, but some things we weren't able to necessarily understand, like what was the temperature gradient in that soil? What was the moisture gradient in that soil? That really seemed to be a very likely driver for the conditions in that roof. And so this seemed like a perfect opportunity for us to take our monitoring platform that we had developed and put it into a very unique application where high density mattered quite a bit. So this gives you a sense of some of the data that we were pulling initially. You can see, for instance, the very nice, clean planting scheme that had been put in by the landscape architect. and then the reality that we were finding about 7 or so years later. So really to understand why became a really important question for us. Just saying it's different didn't seem to be quite satisfying. We wanted to know why we are seeing this pretty remarkable degree of species drift and all these new emergent and volunteer plants. So we deployed a number of moisture sensors on the roofs of these buildings. And what this proved to us is a couple things. One is that we can incorporate other people's technologies. Previously, we had been manufacturing everything ourselves. We had been designing the chips, doing our own reflow soldering, doing all of our embedded hardware programming. But now we wanted to figure out if we could pull someone else's equipment into our platform. And all we really had to do was append this data with a one-wire serial number, and then we were able to pull it into our database because now each one of these had basically a unique name associated with it. So we took a number of these sensors, put them on runs, and then deployed them on a roof over the course of one of our surveys. And we found out a couple of things. One is that this is really hard to do. And it ended up being, I guess you could say, maybe a test of friendships for those that were involved in this particular exercise. But also, it did prove that there was an incredible amount of variation happening on this roof, and there were definite hot, cold, wet, dry zones on this roof that were evident even on the short cycle of a few days. And so this type of data all of a sudden began to point to us that there is a lot of value in monitoring here that can really complement some of the other practices that we're doing. And that this type of monitoring is something that would be incredibly difficult to pull off with any other type of platform. But as I said before, it wasn't necessarily all gravy. It was a lot of challenge. We're using a prototype system. We're up on an unusual environment, a roof, where you're supposed to be tied down. A lot of things that aren't necessarily easy to pull off when you're dealing with sort of an emerging and developing prototype. So we took this as an opportunity to reevaluate what we meant by low cost. Sometimes low cost isn't just developing your own kit. It's actually going back to using something really dumb, really easy, and available off the shelf. And while it may not be the coolest thing in the world, there's a real place for that. And so we had an opportunity at a building that's rather excitingly called 7R, also down in the Philadelphia Navy Yard, that has a green roof installed. And that green roof is one that incorporates a variety of different plantings. And so on that roof, we wanted to see basically what was happening during the emerging of all of these different plants. So we actually were going to be installing these sensors at the time of the roof construction, and then seeing how the emergence of the plants actually altered that thermal profile. So given the close proximity of this project, we took it as an opportunity to use a fairly simple technology, something that's called iButton, that still uses the one-wire protocol, but it uses basically something that you can see there on the lower left. You might see some examples. They're basically these metal circles, and they have a serial number, and they have a data logger, and they have a temperature thermochron that just basically records temperature. And that's it. And each one of those costs about $25. Really dumb, really cheap, absolutely indestructible, has a battery, and you just buy them off the shelf. So we bought a bunch of these and figured it was something like this. Yes, there's no telemetry, but hey, it's near our office. They're really easy to use. We can just send an intern down there onto the roof, and he can pull the data. No problem. So looked at this as a completely new opportunity to deploy them on this roof, where you can see here that things are just starting to bud out. We can get this really transformational phase and understand exactly what is the role of plants. Is there any benefit with the plants? They just make it look nice? Is it just the soil that's doing anything on these roofs? We were hoping that this data would basically start to illuminate some of those questions. And what we were able to find is a couple of things. One is that by using a fairly rudimentary technology, we were actually able to keep costs down because you reduce all this uncertainty. You're not trying to develop your own fancy stuff, but you're actually using something that's just off the shelf that just works. The second thing we found is that we're able to have anyone go down there and pull this data for us. It didn't have to be someone from the research group that might otherwise be engaged. It actually be one of our summer interns. We just sent them down there with a laptop, pulled the data, and then we had that same individual just run up a quick Grasshopper script and visualize this data in space. Pretty easy to do. But the information that we found is actually still really interesting. We're still able to see thermal variation over the site. we were still able to understand whether or not there's any association between the plantings and what we were actually seeing in the data. And we're also able to use this as a mechanism for determining whether or not there was insulative value in the roof by looking at the temperatures at the roof membrane versus the ambient conditions. So this takes us to, in many ways, the culmination of a lot of these efforts. And our most recent deployment, which was an effort to use these technologies in a building at the time of construction. How do you fold monitoring in as an intrinsic part of the overall building concept? So it's not something that's just taped on after the fact, but it's actually something that is instrumental to understanding the building's performance and the building's operation. And the perfect opportunity to do something like that, and that sort of experimentation, is on ourselves. We find oftentimes that experimentation can be messy, and it's not something you really want to include clients on. And we had just bought an old brewery, or actually the bottling facility for a brewery in Philadelphia as our new office. It was a 68,000 square foot facility, and it was one that housed all of this old bottling equipment and had been laying empty for a while. But for us, it would basically be our new home. So we wanted to figure out how we could take that building that would be transformed into this and understand how sensors can be used to optimize performance. And part of that optimization would come through an incredibly high density network. So one in which we would basically look at sensors at the highest density we'd ever deployed them before, so we could understand data from the perspective of what is the temperature at every individual desk that a person might be located, what is the temperature across all portions of the envelope, what is the temperature within the slab, things like that. So we can really start creating incredibly nuanced understanding of this building's performance. So to do that, of course, you first have to deploy a network within this space. So we basically deployed a series of sensors in ribs that were oriented longitudinally within this building. And in each one of those, we had a single node that transferred information, and then a long wire that represented there with a red line, to which we could tap in a bunch of one-wire sensors. And the nice thing about this technology is it allowed us to have basically a single line going to a node, which is quite expensive, and then the one-wire sensors, which are incredibly cheap. You have a number of those using one node to communicate. So we also had them in some of the high bay spaces as part of the overall design, which was dependent upon natural ventilation. We need to understand what was the thermal stratification within that space. One of the things that we also wanted to push for here is how could we take a technology that previously had been pretty crude, pretty ugly, very much so a prototype, and turn it into something that was not only aesthetically appropriate for an architecture studio, but at the same time would be durable for the 20 some odd years that we'd expect it to need to be functional, because we were going to be putting these in spaces that we were not going to be able to get back to for years. We were putting in a raised floor, and you can't drive a very large, heavy lift onto a raised floor. So this became an interesting challenge for us to start thinking about how we'd actually do that. How can you create a sensor that looks decent and at the same time will last such a long time? So we ended up pulling from a lot of our internal resources and our own experience. Once again, designing and fabricating our own hardware, but then taking the extra step of encapsulating it and potting it within epoxy compounds to reduce the risk of any type of corrosion, and then also 3D printing housing for these units that would prevent the accumulation of dust that would affect sensor readings, and then also having an attachment mechanism that would be compatible with the space, in this case using rare earth magnets that allow for them to snap directly to a lot of the metal components that were used to construct this original building. So something that really, in many ways, was actually surprisingly inexpensive. We pulled from all of our own resources, and we're able to use things that were really everyday tools in the architecture office, 3D printing and things like that, that really aren't terribly exceptional. And then, as I said before, we incorporated this as part of the construction process. So this is something where we had a particular phase between some of the trades, and we would come in and we would make use of the equipment and install all the sensors over the course of several weeks. It ended up being really a fantastic opportunity to understand some of the challenges associated with these incredibly high density deployments. And there you can see me sporting some rather magnificent hair, deploying sensors up in those really high spaces. And you can see, this is not an easy space to get to. But getting data up here is incredibly important when you start thinking about natural ventilation protocols and things like that. So ultimately, we deployed a network that had a very strong performance and aesthetic agenda. So you can see on the left, we have some of these temperature readings taken from the large monitor that we have, where they're shielded from radiation, once again pulling from our own 3D printer to basically print a one-piece radiation shield. Then we also have our relative humidity sensors there on the upper right that we fabricated. And then we have the slab temperature, surface, core, and ambient temperatures in the underfloor system that were deployed as well. A little bit cruder, of course, because it's hidden. So all this equipment was used to basically understand how this particular system functioned. So we had a rather novel system deployed at this building, one in which there would be no air conditioning for a building in Philadelphia. I'm not sure how many of you have spent a summer in Philadelphia, but I'll put it rather bluntly, it's hot and humid. And both of those things make for a challenging environment not to have air conditioning. As a mechanism for tempering, we did install a Advantix dehumidification system, which is a lithium salt dehumidification system, a fairly sophisticated one, not typically used in this type of application. You might see it, say, in skating rinks or clean rooms. But it's one in which it's basically as advanced as they get and should be capable of drying out the space very quickly. So the idea here is that we have an underfloor system with two primary highways represented here and here. And those two would deliver a pressurized air through the underfloor system that will come out through a number of swirl diffusers that are located at every individual's desk. This is an unconventional system, one that would be combined with a night flush cycle that would deliver air through the underfloor system to cool down that slab and basically charge a thermal battery that could taper temperatures throughout the day. That was the theory. Here's the wishful arrows of that particular operation. So you can see here that the air will be delivered through that underfloor system, cooling down all of these heavy surfaces, all these massive surfaces, and then it would be vented out. And this would actually happen over the course of potentially in the morning and at night, basically bring down the temperature of that space fairly significantly. At least that was the intent. We had other modes of operation where we would be running, say, the underfloor system and then exhausting some of that air, or not exhausting some of that air through the ceiling, and then some of it also be recycled, potentially tempered, and then reintroduced. And then another mode of operation where you're just bringing in air from the outside and flushing it out directly. Well, this was all the intent. This is what had been worked out with our consultant engineer. It all sounded quite compelling. It sounded like an opportunity to really push the boundaries and experiment with a completely new way of thinking about office conditioning in an environment where typically the rule is sealed up and air conditioned. So would it actually work? Well, as soon as we had the opportunity to begin experimenting, we did. And one of the first things that we did is we started to try to understand what is the capacity for thermal exchange with that slab. Were we on the right track by saying that we could flush this building, bring down that slab core temperature, and use it as a thermal battery throughout the day? One of the things we found out quite quickly by running an analysis of that and looking at that heat diffusion in particular here was that between the slab core and the tile surface, there was an enormous amount of radiative exchange between those two elements. But unfortunately, there was very little convective exchange between the air that was going through that duct and those two surfaces. Well, this was fine for wintertime when your slab might be nice and warm and toasty because you're heating up your building pretty much 24 hours a day. It would be a real problem potentially in the summertime when you're dependent upon this nice flush cycle to cool down that slab. And of course, we would have to wait to summer to find out what that would actually look like. One thing that we did find, however, was that the concept of having a purge cycle did prove actually incredibly effective. We found that we could purge this building incredibly quickly and drop temperatures down all throughout the stratification of that space very quickly whenever we ran a purge. But one of the things we did notice is that the temperatures would bounce back incredibly quickly, and it began to speak to the importance of internal gains. This wasn't necessarily something that had been fully thought of when it came to the assessment by the consultant engineers. But when you have 110 people that are rendering, running computers, a lot of them are souped up, and we have some computers that actually have auxiliary cooling systems because they're running such large graphic cards, things like that. Each one of those, computing power doesn't take any energy. You're basically just generating heat with a computer. That's all you're doing. And of course, you have a bunch of people in the office. You have coffee machines. You have fax machines. Well, I guess we still have one of those, but you have copiers, printers, and all sorts of other things. You're starting to see the internal gains really matter and actually end up being an incredibly large source of energy within the space. So we combined these types of assessments with modeling, as is normally the case, and began to look at some of the CFD models that we had run in these spaces and found that some of the distribution that we were actually measuring with our sensors and what we were modeling showed that we were seeing a pattern of air movement that perhaps was not quite as thorough within the space as we would have liked. Ideally, we would have seen something like this, where we would have seen some purging throughout a larger portion of the space. And we actually used the sensor data in conjunction with this modeling software that we cooked up to determine whether or not there'd be value in installing east side fans. So now we had started to move from understanding and using energy performance data derived from, or thermal performance data derived from sensors, just to understand, say, thermal diffusion and things like that, but also understand potential implications as far as renovations for our building. Now, this is a $100,000 decision right now. You don't want to make a wrong one. You're putting giant holes in your envelope. So by combining thermal data generated by the sensors in association with modeling, we're able to really validate some of those decisions. But of course, at the end of the day, it really matters, are the people happy? And happy workers are definitely an important factor. Of course, happy doesn't always mean the most productive, but our goal is definitely to have people that are looking forward to coming to work every day. So when we start really pushing this type of experimental building, when you're not having air conditioning in the space and you have very unusual modes of operation, an important component of this is to incorporate a survey. So every day, a survey goes out to the staff, actually several times a day, and asks them, are you too hot, too cold, just right, what have you? And what are you wearing? Where are you located? So we're able to get spatially and employee-specific data, including the clothing factor, multiple times throughout the day. And we're able to feed this back to the temperature data point that we have for every location. And because we know where our employee is located, we know the temperature of all the surfaces surrounding that employee, and we know the emissivity of those surfaces, we can create a radiant temperature map as well as an ambient temperature map of the office. So we're able to understand whether or not this employee is in a hot spot. Are they perhaps a thermal outlier? We're able to really fine tune. In some places, we actually can move employees around so that they're in their most thermal comfort sweet spot. But we can also use this as a mechanism for determining whether or not the tools and the means that we have for conditioning our building are appropriate. So part of this all comes back to whether or not the building was performing as anticipated. And one of the interesting challenges that we found was that sensor data fed us some very important information when it came to dealing with some of the consultants when it came to understanding building performance. I don't think anyone likes to be told that their building is not performing the way they said it was going to perform to their client. But we found a lot of pushback from our engineers. The nice thing about having data is it was something that was absolutely definitive that says, the building is performing this way or that. And one of the things that we found is that a lot of the modes of operation that were dependent upon delivering underfloor air through a very large VFD indicated that the compression energy from that fan on that air was actually raising temperatures by about 5 or so degrees of that air that was getting pushed into the building. When you have a 5-degree increase in outside air temperature, if you're bringing it in, plus you have internal gains, it really starts to undermine the effectiveness of an all-passive strategy. And the finding that you're seeing these gains from the fan were not going to happen from the BMS. There were no sensor data points installed in that location. It actually happened because we had deployed a very dense network of sensors throughout the building that allowed us to measure the incoming air temperature and the air at all points when it came out of the air handling unit. So that was for us a really interesting moment. It also is one in which we found that certain modes of operation were not only completely invalid, but other modes of operation were entirely reasonable. And so using this information, we're able to basically create a mode that had sufficient comfort over the course of the summer. But one thing we did find, though, is that we were oftentimes just pulling from only a handful of sensors, even though we had about 400 deployed in this building to make decisions. And so what we realize is that when you start pushing the number of sensors into space to an incredibly high number, it's really hard to make use of it. You know, a spreadsheet or a graph only takes you so far. And so what we began to do was realize that you have to visualize this information in a meaningful way. So what you just saw in this graphic, the video that was playing, was a importing of our data in real time into Unity, which is a gaming engine normally used for creating things like Halo or something like that. And what it allows you to do is to see the data in real time or back in time, and maybe if we're getting sophisticated, maybe a little bit forward in time. But the key here is that you have to start thinking differently about how data is represented when you start to get to this very high density. And in fact, pulling that information into these other softwares is incredibly easy. Well, I wouldn't say it's incredibly easy, but it's a lot easier if you have a database that's storing this information successful through an API. So that was not vaporware. That was actually the information that we imported into a 3D gaming engine. So this takes us to our current state and the question of whether or not we've realized something that had been our vision since its earliest experiments of basically creating data at a very high density that can be visualized or rather transmitted remotely to the cloud and then accessed through a variety of platforms. This was our vision all along. And with this last project, we actually achieved our vision, and we achieved it with a degree of reliability that had not previously been possible. And this is basically takes us to our final evolution. So we started with something as dumb as an Arduino system, sucking power, somewhat unreliable, expensive, going through what I would call sort of our XP days, and then going here to an IPv6, realizing that we were totally out of our element when we were trying to use embedded wireless microcontrollers, way too sophisticated for a firm like us, frankly. And then starting to move towards, at their ultimate evolution, an embedded Linux device that is low cost, easy to use, and at the same time operates on standard protocols, in this case Wi-Fi, that was totally reliable. And we thought, you know what, we have something that works, and it's cheap. We're getting something where the marginal cost per data point is like $8. I mean, you can't beat that. It's unbelievable. And we have a database that works, and we have a front end that people can access and pull data from that's really seamless. And this is something that we've always wanted and we've never found. So we decided to go the next logical route, which is create a commercial product for something like this. And so here you're looking at basically the final iteration of our hardware, one that's now been manufactured, where we're pulling from some pretty dumb stuff. 3D printed housing, but you know what? It's cheap and it looks decent. Still uses a one-wire protocol and sensors that are incredibly small, so you can fit them into tight spaces within a building. And it's one that you can plug in an enormous amount of sensors too. So you have one node that may be a little bit expensive, maybe looking at, say, an $80 item, but you can plug in 3 drop cables, each one 100 feet long, and each drop cable can have up to 30 one-wire sensors attached to it. So all of a sudden, you're looking at a lot of data that can be generated from one piece of hardware, and all of that can go right to the cloud via Wi-Fi. So we're releasing a series of development kits. Right now, we have them manufactured. We're assembling them. And of course, one of the things you realize is it's not just about the hardware. The hardware, sure, it's complicated, and it's nice to have something you can hold in your hand. But the really big challenge with all of this is the back-end component. It's the actual database. And so we realized for any of this to be really reasonable as a proposition to someone other than ourselves, is it has to be a turnkey solution. You have to be able to receive a piece of hardware, open that box, plug it in, connect it to your Wi-Fi, and then you go online and you get your data, and you're done. And that's one of the things that we've done. We've created that whole mechanism. So this is once again, this is actually what you're seeing. This is our current front end. The people, you log on to our facility page that we have, and you can look at all 400 of those sensors. You can see them all reporting. You can see each one here. Each one has a unique serial number. You can aggregate them in any way you want. You can graph them any way you want. You can download the data as CSVs. And of course, when it comes to interoperability, these days, if you don't have an API, you're nothing. So we also have a really well-documented API. So now we have something that really does communicate easily with a lot of other platforms. This can communicate through back to our VMS system. If you want to bring it into your slick Grasshopper script, go ahead. It's easy enough. There's a series of documented queries that you can run. So we have a bunch of these kits. This is down in our research lab that you have. You can see we reappropriate some of the SmartWrap panels as some of our space there. But we're actually putting and assembling the kits right now. I took this just before I left. And you may be wondering, well, why am I talking about these kits? Well, it comes out basically that we have a certain number of these that are going to firms that we like and we know are really going to push the limit on how well these things function. But also, these things, we're setting aside a bunch of them for anyone else that has an interesting project. It's available for free. Send us a research query. Send us a little proposal. Give me a call. The number is there. And if you have something that's interesting and you have some monitoring and you're interested in finding out, can low-cost monitoring, that's basically a turnkey solution, actually work? Is this something I can use? Yeah, we're interested in having you put our equipment through its paces before we roll out something on a really large scale. So I'll end with an open invitation for all of you to basically dip your toes into low-cost, high-density monitoring. Thank you. And any questions from the audience or from the virtual audience? Which one? The one that we're using right now? Yeah, so they're Raspberry Pi. They're running a custom Raspbian script with one wire file system, and obviously the database and whatnot is all running separate types of. But we found that it's incredibly reliable. Raspberry Pi is really cheap. We're looking at other options potentially down the road, like chip and things like that. The code transfers right over. But it's really nice that a lot of people have done the groundwork. Why reinvent the wheel if someone has something that works? So one of the things we were initially worried about with Raspberry Pi is you won't get that long-term reliability, but we've had some that are now running for 8 months continuously. And so we're really pleased with the performance. I think it speaks to some of the remarkable work that other people have done. But basically we have a Raspberry Pi, and then of course we develop a custom shield that goes over it that allows for us to connect all of the sensors to that. No zingers from the audience? Well, I think one of the things that's probably important to note is everyone has different monitoring requirements. We look a lot at temperature and relative humidity because they're relatively easy to do. The sensor technology is accessible and they're broadly applicable to a lot of questions. But there's a lot of other types of monitoring out there that we're interested in as well. Air quality, energy, actual direct thermal transfer, heat flux, things like that. And so that's something else that we'd really appreciate some feedback on. We are able to communicate over I2C, SPI, obviously one wire, and we're interested in other people that have other types of monitoring applications that maybe we're not currently addressing that you'd like to see rolled into this package. So that's something that I would certainly like some feedback on from those that are the practitioners in the field, because at the end of the day, this isn't a vanity project. This is something that we feel is useful and that we hope is useful for others. And so understanding how we can really bridge that gap and make something that's incredibly useful to advance the capacity of the field it may take monitoring from a firm, for something a firm like KieranTimberlake can do, because we feel like spending a lot of money on research is something that any firm can do is really important to us. Yeah, exactly. And that's what we're trying to do right now with our own building. We have found it a little difficult with some elements. When it comes to integrating with a typical system, a typical JACE, that's easier to do through with the API. And we've already done it by incorporating some of our temperature readings as basically components of, or inputs to logic statements that are already programmed into the system. We haven't necessarily used it for the purpose of direct activation, but rather as a data input. We would like to go a little bit closer to that when it comes to things like windows and shades and things like that. But right now, the best opportunity we have for experimentation is our own building. And our own building uses Lutron for all of those components. And that's a little bit more of a closed system. And something that we tried to push for here is really start to understand the importance of open platforms. And obviously, open source is sort of a buzzword. But one of the things that we were actually discussing last night is the challenge associated with having this absolute layer cake, this wedding cake of different standards in your building. You have some things are communicating on Wi-Fi. You might have your Lutron at 433. You might have other stuff that's running on 900 megahertz, and each thing requires its own little base station, its own little database that you have to be pulling from. For us, the real desire is to have as few of these different systems as possible, because all that adds complexity, maintenance, cost. So for us, it's one of the challenges that we feel, and we're hoping that perhaps with the very open, very well documented API, we can start to see other firms that can allow for that type of input into their systems. Yeah, the package, the development kit that we're sending out is what you see here. So basically you get a node, and the node comes not Wi-Fi enabled. It comes with 15 temperature sensors, 3 relative humidity and temperature sensors. And it comes with the types of connectors that are required for all of it. It comes with the wire that you need for all the various components. It comes with a pair of vice grips that are actually used as the crush connectors, because interestingly enough, connecting wire to wire is surprisingly hard when one of the wires is 100 feet long and continuous, and the other one is basically these short trunk cables going to sensors. There's only basically one connector that can pull that trick off, and you need a pair of vice grips to do that. And then you come with the node with all of the software already loaded onto that. And then, of course, you get a password and a URL to take you right to the database. And when you get there, all of your sensors will already be logged. You name them, and you basically can assign them to a deployment, and you're ready to go. And each sensor basically has with it a package that includes its own serial number associated with it, so that you actually know what it is, because there's nothing worse than getting a shipment of 100 sensors and having no idea what each one is called. So, and for those that want more, we can always make more hardware available. Yeah, it's ready. We've already do it internally. We run in things like we've used CO2 sensors. We've done, like we saw the moisture sensor. We've also done some light sensors. We're looking into some of the open energy monitoring as a really interesting platform that goes directly to Raspberry Pi. So yeah, it can be done. Done thermocouples, things like that as well. So yeah, we're ready to do it. I think so. It would have to work. I wouldn't say it's quite as turnkey at this point, but like I said, part of this is really understanding what customers want, and if that's what they want, and we'd like to work with people. So. Call the phone number. Call and reach me. I'm extension 128. Give me a call. I'll be back in the office on Friday. It's really that simple. Is the idea here? We're not holding this in. We're not trying to keep it to ourselves. We want to have people get their hands on it. And it's free, but I guess not quite free. You got to really use it and give us some feedback. Absolutely. And so you can see with the occupant survey, this, looking at this methodology, we started to do that. Our database structure is actually incredibly fluid, and there could definitely be an opportunity to do that, bringing in other types of data. So in this case, we actually did bring in occupant survey data. And I think the biggest challenge is time, making sure that the time data aligns. So your data, sensor data is pretty easy because it's coming in at 5-minute intervals, and it's always 5-minute intervals, and everything's at the same 5-minute interval, no problem. It gets a little more challenging when you have occupant survey. We have, I think, something like 9,000 data points over the course of the summer, and someone reports at 6 a.m., and then someone reports at 7 and 10, and it's all over the place. So there is some challenge associated with that. I wouldn't say necessarily this is something where it's as clean, but yeah, you could have the same data show up in the same database very easily. It all really depends on how you format it. One of the things that's nice about having something like this, though, I guess it would be an interesting challenge, is that the database itself right now only communicates with hardware that we approve. So if your hardware has a serial number that we've vetted and comes from us, then it can go into our database. And if it doesn't, it can't go into our database. So that's something that is part of it, is that a database, right now from our one building, we have 21 million data points. So if all of a sudden it's a free-for-all as to what goes into the database, which is free when you get the sensors, we could be looking at a really significant unanticipated cost. So that's something I think we would have to think a little bit harder about on a very nuanced scale about how to make that happen, because storing data is not so cheap when you're talking about a little bit, but when you start talking about billions and billions of data points, not only is the storage expensive, but also how many requests and polls and sorts you get of that data actually ends up being quite a bit of cost, because there's a lot of computational power associated with culling and reviewing that type of information. Okay, so the offer is genuine, and I really do look forward to hearing from some of the people either in this room or in the virtual audience. And once again, you can reach me here. It's my phone number, and I'm extension 128. My name is Rod Bates. Thank you.